Welcome everybody for this Thursday evening seminar, colloquium. Today we have Minakshi. I don't have to introduce her to you. So she has been a Ramanujan Fellow with us for the last 2 years. So 2 years, right? Essentially, right. And today she'll be talking about Belle II, a precision frontier experiment for uncovering new physics.
Thank you. Thanks for giving me opportunity to talk about my research work. And the title of my talk is here. So before I go into the details of my talk, let me introduce my HEP journey. It has been a beautiful curved road taking me to 5 different countries and working in various exciting projects. So what I'll be talking today and tomorrow, it will be a summary of what I did directly or indirectly throughout my journey. Okay, so this is the outline of my talk. So I'll give a brief motivation to low energy, high intensity frontier physics and the choice of collider and rationale for probing new physics at an E plus E minus machine. And what are the physics achievements of the previous B factories and what SuperKEKB and its commissioning detector is, and then Belle II and its physics program and my plan. Okay, so we know that from the standard model, like what are the fundamental building blocks of matter and how they interact and what gives mass to these particles except neutrino. So, but what the thing that questions all the particle physicists that we have the standard model, what else out there? So for example, standard model has been made incredible progress in understanding our universe, but some of the important questions that remain unanswered, like for example, what is the origin of matter in this universe? And whether the dark matter that is everywhere in our universe, what that particle is, whether it is a particle actually. And do the forces unify at high energy scale or high mass scale? And what gives the neutrinos their tiny masses, and then the flavor. So why we have 3 generations of quarks and flavors, and what behind this strange mass pattern and mixing? So there are many other questions though, but some of them I cast here. Okay, so we have to look into multiple directions, not in one direction. So we have to look in multiple directions. Can be in ground accelerator based or in cosmology or astrophysics. So for example, in high energy particle, in ground accelerator based, in high energy particle collision, we smash things together to see what comes out. Or in cosmology and astrophysics, we watch the behavior of the universe on the large scale or the smallest scale. Okay, so in the ground accelerator based, where we probe the fundamental laws of nature using some incredible machines like Large Hadron Collider, that's the high energy collider which a smash particle with very high energy at a very high center of mass energy of around 14 TeV. Or we go to high intensity collider like SuperKEKB, where we collide particles with very high luminosity or very high intensity to look for rare processes and to search for something beyond the standard model by looking for rare things in a clean environment. So what exactly we are looking for? We are exploring the whole parameter space of new physics and searching for new particles and interaction that lie beyond the standard model. And these new particles can be presented as mass and interaction strength in this parameter space, and our known physics here has a high enough interaction strength, so we can create them at our collider, and it has high enough mass that we can detect them in our detector. And if we go in this direction for relatively high interaction strength and relatively high mass, then we have the energy frontier that Large Hadron Collider is doing. And if you go down relatively lower interaction strength and lower mass, we come into intensity frontier and we look things using intensity frontier machine like SuperKEKB. Somewhere along this line, we have long lead particle which have relatively low interaction strength and higher mass. Okay, so the intensity frontier machine like Belle II and LSCB, they mostly focus on precision measurements to probe things, to probe high-scale new physics by searching for deviation with respect to the standard model expectation. Okay, so this is one example here. Like for example, I took the lepton flavor violation sensitivity in tau decays by taking various examples, like tau can go to lepton gamma, lepton pseudoscalar, lepton scalar, lepton vector, 3 lepton, lepton 2 hadron and lambda hadron. Okay, so if you look at this sensitivity, Belle II has this is the Belle II projection limit, and this is the measurement that has already been done by other experiments. This is the projection. If you look here, LSCB can probe only tau to 3 mu1 decay, so it's sensitive only for that, but other things can be done only at Belle II, all these rare or even like impossible, that is standard model, that searches can be done at Belle II. So if we see even a tiny signal, that could be a clear indication of new physics possibly coming from much higher energy scale. So if so theoretically, first LSCB, so for example, I'll talk it maybe in the last slide. For example, tau to 3 mu1, they have very good muon identification efficiency than electron identification or whatever, and I think they have a lifetime bias trigger, so that's why they are not good at all these things except the 3 muon channel. But given that SuperKEKB has a very clean environment and it can search all these things, and most of the things also involve pi 0, gamma, all those things. So and electron, all these things makes like all these things can be well identified at Belle II than LSCB. Okay, so it's not just a theory. We have example from history, like charm quark was predicted to explain the suppression of this k along to mu decay. So, so this came like whereas the discovery of charm quark came later in 1964. That explained why this k along to mu decay is suppressed by this G mechanism. Okay, so another example, for example, prediction of top quark. So back in 1987, the large mixing rate that observed in B0 bar, that predicted there has to be a high mass particle in the loop that is affecting this behavior, and that was predicted to be the mass of top quark to be greater than 50 GeV, which was later discovered in 1995. So, so from experience, we know that indirect effects in precision experiments can lead us straight to the major discoveries. Okay, so the question is, are we in a similar situation with the current hint of anomalies? So I picked up one. The reason is I directly or indirectly worked with that. So, for example, whether the lepton universality is at risk. So what is lepton universality? The weak coupling of leptons of different generation are the same in the standard model. So, for example, if we look at the heavy lepton coupling to the branching fraction of this B2 D star tau nu to D star L nu, what standard model predicts is here. But what we are seeing from the world average from all these experiments is here. So there is still a 3.8 sigma tension in semi-leptonic B decays with tau leptons. So it's hard to say that there is trouble with trees, but generally we say tree is clean. So time will say when we have more statistics at Belle II. So it's something time will say, and if we compare with LSCB, it's hard to say because if they are not so good at electron, because the machine they have Bremsstrahlung photons and they have to recover those photons. So the good thing, the good machine that we can test all these things is at Belle II. So though it is at 3.8 sigma, it's not yet a discovery, but it's worth watching. Okay, so all these puzzles in our table. So the question is, what kind of machine gives us the best sort of answer to all these questions, and what particle we choose? We generally choose stable charged particle, whether at LSC or SuperKEKB. So at Large Hadron Collider, we collide proton, which are composite particles, and we go up to very high energy. But the thing is, we can't search for heavy particles, very heavy particle, but the collision environment is messy. Whereas at SuperKEKB, we are at limited around 10.58 the epsilon 4s or epsilon 5s mass energy. But given that it's a E plus E minus collider, so the they collide like point-like particles, so they have well-defined initial state and the beams are not strongly interacting, and hence we have low background. And then these are ideal for rare decays and neutrino inclusive final states. And what kind of precision measurement we will be doing with these machines? We can measure absolute blanching fraction or CP violation or mixing related parameters, and we can probe new physics by looking at the deviation from standard model expectation. And given that it mostly operating at epsilon 4s, so we have the powerful reconstruction technique, and we have the ability to reconstruct the full final state because epsilon 4s goes to 2b and they are correlated. And we can effectively reconstruct, find the mass, missing energy or missing mass of the neutral particles. Okay, so so since I introduced you to CP violation, yes? So yes. So for example, it's running. It can run like generally we look at epsilon 4s resonance energy. We can go up to epsilon 5s. Belle has taken some data at epsilon 5s to do Bisaway's physics. But we have to tune our machine parameters. So, but some physics can be done. We will run at epsilon 5s given that Belle has done it already. But we will not take that much of data, maybe 10 times smaller or 20 times smaller data than epsilon 4s. Sorry? 5s we can do, there are many physics motivations to take. So so we have to tune the machine parameters. That is very expensive. Most of the physics is like Bisaway's physics can be done at LSC. They are doing quite well, LSCB. Okay, so since I introduced CP violation, why CP violation is so important? So that comes from this matter-antimatter puzzle. That's Big Bang created equal number of particles and antiparticle, but what we see in the universe is mostly matter dominated, no antimatter. So if you look at the baryon to photon ratio determined from this microwave anisotropy, for each baryon we have around 2 into 10 to the power 9 photons. That means almost all matter annihilated with antimatter, but not all of them. So to explain this, Sakharov showed that that generation of a net baryon number requires these three conditions, like baryon number violation process such as proton decay, and difference in interaction rate for particles and antiparticles, that's the C and CP violation. And in the standard model, we know the baryon number is conserved, and we have CP violation, but the strength is very small, like 10 times smaller than what is expected to explain this matter-antimatter puzzle. So this is the standard model prediction of order of 10 to the power minus 20. So I'll explain so how it is coming out from the standard model. It's from the CKM matrix triangle that I'll talk in a little bit. So that means we should look for physics beyond standard model if you want to solve this matter-antimatter puzzle. Okay, so how the standard model actually predicts CP violation? It starts in 1964 when Cronin and Fitch first time observed the CP violation in the K long system. That K long mostly goes to 3 pi, but there has a branching fraction of K long to 2 pi of order of 10 to the power minus 3. So to explain this, Kobayashi and Masukawa proposed that there has to be third generation to observe CP violation. That time there was no third generation, even the second generation was not complete. So with this third generation, we can explain things in the CK called CKM matrix behind their name, and that each matrix element, so how the quarks change their flavor via weak decay, and this is a 3 cross 3 complex matrix, and it has 4 parameter, 3 mixing angle in one phase, and that phase that appear here in this matrix element, which is responsible for CP violation because that's complex. Okay, so in the most intuitive form, we can write the CK matrix using the Wolfstone parameterization like this. where we have the parameters A, lambda, rho, eta, and this single phase eta generates the CP violation in the standard model. Given that it's a 3x3 unitary matrix, so we have all total 9 relations, out of 6 can be represented as triangles in the complex plane. One of the triangle is this that can be represented like this, when the sides and angles can be well measured through B decay. So this is an important triangle, and the angle, for example, the phi 3 gamma, which contains the phase of this VUB, or the beta that contains the phase of VTD, and phi 2 which is the complex argument of combination of those two phases. So we have to measure all these things properly, and the amount of the triangle, the area of the triangle will say about CP violation, that is in the standard model. But if we suppose have a 4th generation quark, then we will have a quadrangle of more area. That means we can maybe we can push we can understand more better about the CP violation in the universe by increasing decreasing the difference what is predicted by standard model. Okay, that's for new physics. Okay, so there is another way, that's flavor changing neutral process, that's a proof for new physics. So we know that flavor changing neutral processes are absent in the tree level decay tree diagram, but occurs through higher order diagram, and hence strongly suppressed in the standard model with branching fraction between 10 to the power -7 to -4. And it's a good proof to new physics that comes from much higher scale. So example of flavor changing neutral processes that can be probed at Belle II include like B2S gamma, B2S LL, these are penguin diagrams, or B sub S2 mu mu, that's a kind of annihilation diagram, box diagram B2S LL, so, or B2S mu mu. So all these things. So we can, using these flavor changing neutral processes, we can measure branching ratio and test the lepton flavor universality like RK star, all these. So there are many processes where we can study also CP violation and all. Okay, so another question, that we think that the new physics must be at very high mass scale, probability EV scale. But what if the new dark matter particles are in the same mass scale as the ordinary matter? That is where the Belle II can probe in this mass range in the MEV to GeV range. That Belle II is taking that opportunity to probe for new particles in the MEV to GeV range. That's kind of dark matter mediator through different portals, scalar, pseudo-scalar vector, or now we say neutrino portal. Okay. Okay, so let me, the Belle II didn't start on its own. It was it's sitting on the soldier of two successful experiments like Belle and Babar. So those again were built on the success of older epsilon 4 experiments like Argus and Clio. It's a high luminosity EE collider at a center of mass energy of 10.58 GeV, and the goal was to test the standard model CP violation mechanism that was predicted by standard model. So in 2001, Belle and Babar discovered CP violation in the in B meson decays, and for that Kobayashi and Moscow awarded Nobel Prize in 2008. The experimental confirmation by Belle and Babar led the Nobel Prize to Kobayashi and Moscow, who predicted third generation of quark and CP violation. Okay, so that is where the E plus so Belle and Babar didn't stop. They did impressive number of discoveries and observation of rare decays afterward. For example, I have noted here some of them. Like it discovered CP violation, it measured the CKM matrix element, observed BB bar mixing, then observed rare process and flavor changing neutral current process. It's testing the lepton universality and looking for discovery in exotic final states. Did the discovery. So, and prepared the, most importantly, it prepared the stage for the precision flavor physics. Okay, so it will not be good if I say the B factor is Belle and Babar. So LSCB came late into the picture, but it did a fantastic job in discovering many new composite particle in precision standard model physics. And most importantly, in 2019, it observed CP violation in the charm sector. So many things. Okay, so this is the CKM picture over the years when in 2001 when CP violation was established. This is the picture of CKM triangle, and this is where we are in 2023. So over 22 years, it has made a tremendous progress and achieved a remarkable precision. But there is still room for new physics contribution. So it's a combined effort from Belle II, Belle II now providing some result, but most importantly Belle, Babar and LSCB. So together they are advancing flavor physics and search for new physics at multiple fronts. Okay, so since I say there is still room for new physics, so how we search for new physics from the this triangle? First, we have to constrain them from tree level process and loop level process. Tree level process, for example, we look at the gamma, CKM angle gamma, that can be only measured via tree level decays, and VUV, that matrix element, that's from V to pi L nu, for example, that's a tree level process. We expect that tree level process doesn't have new physics in it, and look for the same triangle apex, this one, by measuring the loop level processes like sin 2 phi 1 from B0 B0 bar mixing and decay, then vis-a-vis mixing, then K0 bar mixing, and we will constrain this apex, and we compare at the end when we have good precision, we compare both, and if there is a potential deviation, then it can we can probe for new physics in the flavor sector by looking for the deviation. Okay, so this is brings me why we need even a better E plus E minus flavor factory. That's a high precision measurement of CK matrix, and look for new CP violating phase in B and D decays, mostly charm decays now I am interested in, and imprint new physics in flavor changing neutral current processes, and whether new physics in charge current interaction, that we have to see via this searching for lepton flavor non-universality or lepton number or lepton flavor violation. Again, tau sector, which is Belle II, is the best, and the dark matter. Okay, so SuperKEKB, now I start, sorry. So it's an intensity frontier flavor factory experiment at world's highest luminosity collider that collides electron of 7 GeV with positron of 4 GeV at a center of mass energy mostly at 10.58 GeV. So at a bunch crossing rate of 250 megahertz, that's 4 nanosecond. Okay, it's situated at KEK Tsukuba campus, and it's a 3-kilometer ring. Okay, this is how SuperKEKB looks like, and at the collision point we have the Belle II detector, and then it's a big collaboration with around 1,300 members from 125 institutes and 26 countries from all over the world. India has 63 members from 11 institutions that are contributing to Belle II, and IISc is now officially an official member, and I am serving as the institutional representative. And given that Belle II handles 100 petabytes of real and simulated data, to store those data we have 65 grid sites all over the world, including some key centers in India like IIT Guwahati, Tata Institute, and IIT Hyderabad probably, yeah, and this University of Petroleum and Energy Studies. Okay, so we say SuperKEKB collider is a high intensity collider. How intense that is? This is the peak luminosity. What is achieved as of now is the latest record, that's 5 into 10 to the power 34, and the second best is LSC, it's at 2 into 10 to the power 34 now. And what we are targeting is here, we want to go 8 to 10 to the power 35, so that when we increase this peak luminosity, we can achieve this 50 inverse autobahn. That's our first target to reach at Belle II. But where we are now is very small statistics with 500 inverse autobahn, like 0.6 inverse autobahn. But still, given the machine is so beautiful and our detector is so precise, so we are doing very precision physics and already published 75 world leading publications despite such limited statistics, and more on the way. So how SuperKEKB actually achieve this high luminosity? So how we get number of collision per second, which is luminosity, which is a machine parameter, and we look at the cross section. Okay, so the luminosity we can increase if we can increase the number of like bunch current and reduce the beam cross section at the interaction point. So KEKB has achieved this vertical beam size KEKB was around 1 micron. What SuperKEKB is trying to get is 50 nanometer, which is 20 times smaller, so that we can, the cross section itself will increase the luminosity 20 times more, and we increase the current 2 times, so that we can increase the 40 times instantaneous luminosity. So as I said, in KEKB colliding, these two beams were already much thinner than a human hair, that's 1 micron. Now we are trying to increase 40 times than the instantaneous luminosity, which you have to make the beam as thinner as like 100 times 100 and like few times 100 atomic layers. So that's so precise, so that our beam spot size will be so precise. Okay, so that's very good that we can do very good physics if we go to higher luminosity. So the main challenge we have to deal with is when we have high luminosity, when we have high event rate, we have high machine background. So it can, so when we have high machine background, it can damage our detector due to occupancy in the inner detector and fake hits and pile up. So these are some of the machine related background that I picked up. One is beam gas, beam scatter with the gas, and the Taos check intra beam scattering, and then radiative Bhabha or 2 photon processes. So I worked around more than one, similar to LSC, 10 to the power 11, Okay, so I worked with this beam background detector for around 1.5 years. That was the major project when I started my postdoc. Okay, so this was my contribution to Belle II commissioning detector, that's the pin diode system. So I prepared like 64 pin diode, 32 pin diode modules, like 64 pin diodes to be installed at different locations around the beam pipe. And I installed them here. That was the project of Wayne State University. That I was the only postdoc, I was leading that project. Okay, and monitored the system and calibrated and analyzed the data with this radiation monitoring system. And I actively participated in the commissioning and decommissioning of this beam background detector that we call BEAS2, and monitored the beam background using this pin diode system. And this is what I achieved. So for example, I installed all the pin diodes at different locations along the beam pipe, along different G and different phi direction. And this is how the beam pipe, the area looked like after the installation. And there was a lot of cabling I had to do, like 32-meter long cables, like 64, and thermocouple cables, another 32. So I have to take with the help of others definitely to our DAQ room. So that was just a challenge. It's after decommissioning, you can see all the cables that was mostly from pin diode. Anyway, so what it measured the different pin channels. The highest dose that you see during the 3 months operation, it observed around 200 kilorad at the interact IP area at Z is equal to 0 at the exactly at the IP. So it separated injection and non-injection background without injection, and most importantly, my result corrected the simulation which predicted that the integrated dose has to be much lower, but what I see is much higher. And then to study synchrotron radiation, I had a gold plate covered and one diode to separate if there is any synchrotron background, which eventually I didn't see because there was no focusing magnet that time. Yes. So yeah. Okay, so after the successful installation of BEAS2, this was a picture of the then Belle II spokesperson. So thanks to the groundwork laid during this commissioning, Belle II is now ready to push the boundaries of the standard model. Okay, so this brings me to the Belle II detector, which is a precision instrument for searching for new particles. It sits at the collision point of E plus E minus beam. The beam pipe radius is around 10 millimeter, and the PXD next to the beam pipe is our silicon detector. One is pixel detector, another is silicon vertex detector. The pixel detector has 2 layers at a distance of 14 millimeter and 22 millimeter, followed by silicon vertex detector of 4 layers. One of the layer made by India. So at a distance starting from 39 millimeter to 135 millimeter. So the whole system PXT plus SVD is used to measure the decay vortex of the decaying particles, the short-lived particles, and it achieved a vortex resolution about 15 micron. Okay, so this is complete, this is the old picture. Okay, next to this system is our drift chamber, which is a gaseous detector which is used to measure the particle tracks and measure the momenta of charged particle, and also contribute the low momentum PID. And next to that is our dedicated PID detector. In the barrel region we have the time of propagation counter. In the forward end cap region we have the aerogel imaging Cherenkov detector. Okay, that is used to separate mostly cation from pion, and also it contributes to separate other particles, charged particles. After that we have the electromagnetic calorimeter. It's a cesium iodide crystal, cesium iodide with thallium doped crystal. So it has a radiation length more than 17x0. So it eventually absorbs all the electrons and photons in it, and given that electron is charged, we can draw the track, and it provides a resolution from 4% up to 1.6%. Next is our, the last one is our K-long and muon detector that identifies muon and separates K-long. Okay, it's a hermetic detector, and it has well-known initial condition. As I said, it has low background because it's interacting weakly the E plus E minus, and it has excellent PID system, and we have dedicated triggers for low multiplicity events. When I say low multiplicity events, that's the event that has less number of final states. Okay, so this is the data taking rate. The collision happens at a 250 megahertz, and our high level trigger take it at a rate of 10 kilohertz. Okay, so with all these 7 detectors, we can say what actually happened at the interaction point. As you can see in this picture, our electron and photon are completely lost in our ECL, and the pions, charged pions, will go up to KLM and get lost there. And muon, it's a low minimum ionizing particle. It will pass through all the detectors. And K long, it will not. It's a neutral particle, will not have a track, and that way we can separate. Okay, so most importantly, I will go through one detector. That's the vortex detector of Belle II. That's a pixel detector plus silicon vortex. As I said, it's used to locate primary and secondary vortex of short-lived particle and contribute to the low momentum tracking. And this is what has been measured Belle II impact parameter resolution in the G direction or in the in the XY plane. This is the resolution that has been achieved, the impact parameter resolution of around 20 micron by our vortex detector. And if you look at the short-lived particle, for example D0, which goes to K pi, it measured the vortex resolution at a precision of 40 micron. So, which is twice better than what Babar and Belle achieved, since the vortex resolution is so good and we can measure the lifetime very precisely. That's what you see here. That's the result from Belle II. That's the lifetime measurement of charm measures, for example. So, if you look all these 4 pictures, the Belle II measurement, Belle II measurement, Belle II, Belle II, with very low statistics, and that we have provided in all cases except omega c. Belle II has made world's highest precision measurement in some cases after 20 years, which LSC cannot provide. However, LSC, for example, provided for Desabes case, but the Belle II precision is much better than LSCB. So I was thinking why LSCB could not do that, which it could have done. Maybe they have the lifetime bias trigger, which we do not have. So that's why. And then the omega c, for example, so LSCB has a very good precision, but why Belle II measured it? Just to confirm that there's longer lifetime that LSCB is seeing. So Belle II confirmed that LSCB what is seeing longer lifetime or omega c is correct. Earlier the longer lifetime was here, but Belle II confirmed LSCB. Okay, so the Belle II can make precision absolute lifetime measurement because of the large charm sample that we have without the lifetime biasing trigger, and we have excellent vortex detector alignment, and we have very good vortex resolution, and we have a very small beam spot size. So all these things in hand, and given the precision you see so good with such a low statistics, That means we will be very good at charm mixing and CP violation, indirect measurement of CP violation that has never been observed yet. So it's project like we should do such kind of measurements at Belle II and provide competitive results. Maybe we'll see CP violation in charm mixing soon in near future. Okay, so physics, let me start why it is called a flavor factory. So if you look at these pictures, that's the cross section versus E plus E minus energy scan between 9.44 GeV up to 10.6 GeV. So you see all these resonances, epsilon 1, S2, S3, S, here is 4S. So these are Bottonian states, which is like BB bar bound state, which is QCD instead of QED, something similar to positronium, which is E plus E minus bound state, or hydrogen, which is a bound state of proton and electron. Okay, somewhere here we take data because we want to produce two Bs, because this has much lower mass, so we cannot produce B out of two B pairs. So epsilon 4S is just above the threshold of production of 2B. That's why we are taking data here. So this peak gives a cross section of E plus E minus to 4S at 1.1 nanobar, and below that is continuum, where we have similar cross section for E plus E minus to CC bar, E plus E minus to tau tau, E plus E minus to mu mu, and for E plus E minus to 3 gamma, all these things. So that's why, since we have similar cross section for all these processes, we can do physics related to that. So it's not just a B factory, it's a flavor factory. We can do all, not all, like tau flavor, charm flavor, or B flavor, not flavor, low multiplicity physics using gamma gamma gamma, or all those. Okay, so this is Belle II has a very diversified physics program. This octopus diagram shows all the diversified Belle II programs. What I am interested in is highlighted in this yellow structure band. So what I'll be talking now, most of it, and I'll try to cover some of it tomorrow. So first let me start with the extraction of phi 3 or gamma from this B to charm decay. So it's a standard model benchmark channel because it's a tree level decay, very little theoretical uncertainty, and it's the only CKM angle that can be measured via tree level decay. And so if it precisely measured, it can set a very strong constant on the standard model. So if you look at this diagram, so for CP violation to occur or to measure the complex phase, we need at least two amplitudes that goes to the same final state, two paths, so that there is interference and we can extract. So for example, if B goes to a final state, particularly this, we can either have suppressed diagram contributing, or the favored one. This is the favored one, this is the CKM favored diagram, or the suppressed, which is both CKM suppressed as well as color suppressed. But it contains the phase information here, VUB, that's the complex phase. So we measure this amplitude ratio for these two processes, which depends upon the ratio of amplitude or magnitude of suppressed to favored amplitude, and strong phase and weak phase, and we have many final states, B going to D processes, and many final states. So we require high statistics. If we combine in more experiments, if we combine all the results, we can constrain phi 3 to a very good precision. So this is the precision that phi 3 has achieved at Belle II and Belle, and using many channels, and that's about 7 degree. And so I contributed a lot to this physics project during my PhD or afterward, or while I was a convener in this physics group. And then if you look at the global picture, now the global average is around 3 degree, which is dominated by LSCB measurement. In fact, to this global measurement, I have contributed indirectly, I would say, because I found through the Clio measurement, I found the CP content of D2 pi 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 0, K pi 0, and K3 pi. All these measurements using all those channels, LSCB now doing precision measurement for phi 3, even though Belle has not yet tried those. So that way I have contributed to the world average other than what I did at Belle II. So now the world average is dominated by LSCB measurement. So it will be exciting time to come back after Belle II reaches 5 inverse vote over net least. So much. This one, sorry. Yes, this is the world average that's LSCB dominated. They are doing much better this physics than Belle II now because we are constrained by our data size. World average means it includes the results from Belle II, Babar and LSCB, but LSCB is doing really great. It single-handedly achieved around 3 degree or something. Is that your question? Yeah, result is dominated by LSCB. Oh, you are asking about the central value? We should not look at the central value but the precision. Yeah, so it's a combination, combined result. So it's a combined result from all the experiments and from all the channels. Yes, you see 7 degree, and this we should trust more to world average, the average. We cannot. Precision, lower precision than LSCB. Yes, that time we will say where the central value moves. Okay, so this is about B, hadronic decays of B. And what about the semi-leptonic decays where we have, for example, one neutrino in the final state, how we handle that? So identifying semi-leptonic B decays, I did this work for the, when the early Belle II, using early Belle II data, for the first time I measured the branching fraction branching fraction measure. I provided the branching fraction, first branching fraction of Belle II using this channel. And how I did, I used an on-tagged approach. So given that we are producing 2 Bs at epsilon 4s, on-tagged approach means we will look at one B, we will not care about the other B. That way we will have higher efficiency, detection efficiency or signal efficiency, even though we will have higher background. So in the untagged approach I used and look at the B to DL where B is at rest and measure the missing mass, and using this Y system, that's the DL system, and this is how the missing mass look like. It's in principle it should be at 0, given that neutrino has mass so low that Belle II is in GeV scale and it's in EV, less than EV. And then another variable is cos theta by, that's the angle between signal B and Y system using a constant that mass of neutrino is 0. That's this plot, and the signal is expected to peak at this between -1 to +1 and background all over. So the distribution looks little broad due to the beam energy sparing at the start of the experiment, but it still provides a useful background signal background discrimination, and I measured this branching fraction just doing a 1D fit to either cos theta by or missing mass. So if you want to do a better precision, we can take the lepton momentum which is very high in the system, so missing mass versus lepton momentum, and fit it and see the signal. Okay, so my result is here. That's a Belle II on-tagged approach that I used, and this is the world average, and this is my result. Even though with such small statistics, the result is so good. And hopefully using this branching fraction and doing more precise measurement, we can say something, measure the VCB and explain the tension that persists between VUB and VCB through inclusive and exclusive way, something like that. And then the tagged one, that was done by Belle II. So if we can do the same in a tagged approach, that we reconstruct the 2 B measons. For example, one with the tag B meson we fully reconstruct and the neutrino is missing on the signal B. Still it's similar to the full reconstruction like an hadronic event. Even though single missing particle is there, it's as clean as getting all particles measured because we know the initial condition and we have the information of the tag side B. But the price we have to pay, that the efficiency will be lower. And with a little bit higher statistics, Belle II tagged approach, they found little worse precision than the untagged approach that I had. So that's what it says. Okay, so how we handle more missing particles, suppose 2 neutrinos. For example, B to S nu nu, B to K nu nu or K star nu nu. So that can only be done at B plus E minus B factory, not at LSCB. And this is good to search for new physics using this channel, given that it doesn't have hadronic uncertainty. So it's allowed in the standard model as you see here, but very sensitive to VSM. And this is challenging experimentally, given that very low branching fraction, larger background, and no signal peak really. So yeah, So this is a picture, simulation picture though, how the signal B nu nu look like in the RZ plane and in the R5 plane of Belle II. So it has been tagged using B2 d pi, the slope ion say curling in the CDC, and the kaon and pion that comes from this D, they are going in this direction, and the neutrino here in the kaon. Okay, so it's a very complicated analysis that yeah. So, momentum is only by our tracker CDC. That's good enough. Momentum for the momentum. That's a good question. We look at the momentum, in some way infer the information by missing mass technique, K long for example, but mu1 is good. But K long is the only thing that's the only hadron that, but we have a way to do analysis using that, and we have done that. Okay, so it's a complicated analysis. So what I would say that signal candidates, if you look at how to discriminate signal from background, so we usually use event shape and the kaon momentum. So the QQ bar, which are jet-like back to back, they will look like this, the event shape, BB bar symmetric, and K nu nu 1B is like this. If in the case of K nu nu, it will look something different. So use event shape technique and use this machine learning to do this analysis, and we take into account that kaon that comes from B, just one charge track and 2 neutrinos, so that's energetic. And using this, and we use two different methods like inclusive tagging. On the tag side, we include everything, semi-leptonic decays, hadronic decays, everything. On the another approach is hadronic tag, that we just take the tag B decays hadronically. So in that hadronic decay, we have efficiency less, and inclusive tag, we have more efficiency. So this is the result that Belle II has provided with such small statistics. This is the inclusive approach. This is the inclusive approach. So what we see, the combined result from both hadronic and inclusive approach is here from Belle II, and the combined result evidence is at 3.5 sigma. So we have not yet discovered, we'll soon discover this B2K nu nu decay, and there is a tension with standard model at a rate of 2.7 sigma. So that time will say many questions. Okay, so now I move to heavy axion like particles. I just picked up one or two for the new particle searches in the MEV2GeV range. So I'll tell you why I picked up the heavy ALP that can connect standard model to dark matter particles, and this analysis has been done at Belle II using E plus E minus to 3 gamma final state, 1 gamma and 1 axion, and axion to 2 gamma. It's a 3 photon final state, and the statistics used around 1200 times smaller than what we have now. It's used very small statistics, and we select events with 3 photons, and we look for a peak in the diphoton invariant mass spectrum. And this is the, since the axion couples to gamma, so we provided the axion to ALP to diphoton coupling as a with respect to mass, and this is the Belle II limit with very small statistics, as I said, with 1200 times smaller statistics when it was doing. And this is the Belle II projection that it wants to achieve with all its statistics. And so our result is most restrictive in this region, 0.221 GeV. Okay, now I go to heavy ALP. That's not photon to axion coupling, ALP coupling, but it's a gluon coupling that we search for in the process B2SA, where the axion couples to gluon and axion decays hadronically. So this kind of search can be done at Belle II, and if you look at the parameter space around 400 to 900 MeV range, where this axion is seems to be long-lived in this C tau range. So I am interested particularly that because I am interested for long-lived particle searches, and I picked this A to 3 gamma, 3 pion final state because that has a very good branching fraction on the mass range I am looking for. and it's a 3 pion final state, 2 charged pion and a pi 0. Given that this 2 charged pion, so we can find the decay vortex, and we have a very good tracking volume, and we just from in this G direction, this is the tracking volume of our drift chamber, and in this in the R direction, this is what. And so this A to 3 pi final state is kinematically allowed for mass around 400 to 900 GeV, where for which the action is long-lived. This is a paper, a Feno paper that I liked and I want to contribute when I have person power. That's on my to-do list as an experimentalist. Okay, so this is brings me to a projection of Belle II and comparison with LSCB for few channels. As I said already, LSCB has a lot of heavy B mass, like heavy B events. So they are good at B sub S physics, and particularly B sub S to mu mu, given that they are good at muon, identifying muons also. So that's why Belle II will not be competitive for that, and we are not, as of now, we don't know how much data we will take at epsilon 5s. And also for B0 to mu mu, they are also good at, given that muon channel. And all the B sub S physics, they are good, and B0 to EE, for example, that's Belle II will provide more strict limit than LSCB, probably much higher, like 100 times more. And some tau physics that can only be done at LSCB, for example, Belle II. For example, tau to 3 mu1 final state, though LSCB can do, but you see, so comparing like 1 inverse femtobarn at LSCB is same as the 1 inverse autobarn at Belle II. So they are still not good at this measurement. It will be Belle II will be 100 times more precise than what LSCB can do. And for the true neutrino final state, all these B to K star nu nu or K nu nu, only Belle II can measure. So this brings me to the comparison between LSC and LSCB and Belle II. It's a competition or a complementarity. It's a friendly competition. So, and look at the property. So even though we have very low cross section, like LSCB has huge cross section, but we have high luminosity, and we have low background level, we have high efficiency, identification efficiency. Initial state is well known. Even though decay time resolution is not excellent as LSCB, but we are, it's very good. And collision spot size is very small, tiny. And we can identify K-sorted pi 0 efficiently, which LSCB cannot do. And we have very good flavor tagging efficiency. And so this makes, this property of Belle II makes the physics capability of Belle II excellent, whereas LSCB is limited. Sorry, yeah. So this is all I want to say. And this is my research interest and group that I want to say in a few minutes. So my current research plan, I'll talk tomorrow about heavy neutral electron search, and then direct CP violation time independent search, because I'm using charge D, and at Belle II I'll cover tomorrow, and then precision measurement of charge mixing and search for time dependent violation at Belle II. That's my current research interest. And additional research interest, I want to do heavy LP search at Belle II and search for LP, long lead particle in dedicated experiments, including Belle II, that I am very much interested. And some Feno work I am doing on RPBB and baryon number violating neutrino in B and tau decay, that's again long lead. And plan is to contribute India's effort and the Belle II SBD, that's led by TIFR, where students all over the India working in Belle II, they are getting trained in hardware and detector technology, and further small scale hardware projects can be brought to the IISc for students' interest. So these are the students currently working with me. Nayana is working project associate, working on the direct CP violation measurement, and one undergrad student will be working on this CP violation in hadronic B decay. So another undergrad student who did his UG thesis completed, worked on this precision measurement of charm lifetime. So he was offered admission in 2 different good university on the data science, master in data science project. So he will be moving, so he completed his bachelor thesis. And another student is currently working, he is 3rd year student, And Adam Libby, he is from University of Oxford. He will join for his master thesis. He'll be visiting in July for 3 months to work on this jar mixing at Belle II. And one of our experimental student, Aman Sahu, he is selected for this KEK summer student program, which is very, very competitive to get. That's good. And research plan, I am currently doing my work with the available funds under Ramanujan Fellowship. And Belle II is included in India's Mega Science Vision document. And we have submitted joint funding proposal to DST and DAE for common funding to support participation in Belle II. And IISc is already in the list. And 5-year budget request is done already 125 lakh for a period of 5 years. Once Josna joins soon, it will hopefully get double. So the 5 major goal of the proposal to conduct high precision study and search for signs of new physics at the intensity frontier. And the detector system, it's not limited that people have to work on silicon. Whatever people are interested in other detector like drip chamber or this Cherenkov detectors, they can participate. It depends upon the student's interest. And train researchers students in advanced particle detector technology as well as grid and cloud computing and machine learning for big data analysis, which I'm doing for our students who are working in Belle II for their master or bachelor's thesis. So it should strengthen India's visibility and leadership in global picture in global particle physics community. That's all. I want to thank you with the Belle II detector. Thanks. It's not a dark matter particle, given that it's heavy. So it's a it's a pseudo scalar. Yeah. So it's a. So they provided different coupling G to A, like A gamma gamma, or the measure this FA. What is that constant? I forgot the name. Yeah. Yeah. Yes. End of my talk? No, beginning of my talk. Oh, Alp decaying to 2 photons. Sorry. One moment. Yes. Oh, I could have stated that, but I don't think there is a picture that combines all the measurements. But okay, sure. Yeah, sure.